Good morning, everybody. Let's get started with public key infrastructure fundamentals. So the goals of this lecture are to understand how you can distribute public keys. So cryptography is all about moving protection of information to keys. And at first, at least with symmetric cryptography, and it's about moving information to secret keys. But then, of course, because secret keys are kind of hard to distribute, it's especially on a large scale, and you have a very big risk because you end up with a database of secret keys. What you would like to do is public key cryptography. So for large-scale crypto systems, we usually have public key cryptography, although there are exceptions. One exception is the GSM system, which is actually a huge scale system with billions of users. It's based on symmetric cryptography. But at least for open systems, because GSM is closed in some sense, you only have security between you and your operator. There is no security between you and the recipient of the call anywhere in the world. So for large-scale systems, you need public key cryptography, where you move protection to authenticity of public keys. And this seems to be kind of easy, or we thought it would be very easy. I think in practice it's quite hard, because this is where you really end up interacting with real users and real systems and real organizations and structures. And so I think in some sense cryptographers have been very naive. We thought that we could bend the world to our view of how public keys should be distributed. Of course, it should be the other way around. You should organize how you distribute public keys according to how the world is organized. And the world is complex, so this is also a complex problem. So I hope most of you already know something about certificates, but we'll go back in detail to explain you what the CA does. And of course, the big problem with CAs, or certificate authorities who distribute public keys, is that there is not one. If there was one, the world would be easy. But the problem is there is many, and they all operate in a different way, and depending on the application sector. So there is a range of them, about 60 to 70 for the internet. There is some for the financial sector, there is some for the government sector, and so how can all these interoperate? But so, in general, there is many ways to distribute public keys. So between people, it's pretty easy. Cryptographers are maybe an exception there. So many cryptographers just print the hash of their public key on their business card. And so in fact, if you meet them the first time, you actually get the hash of their public key. And then later on, they can email you their public key over an insecure channel. And you can then, if you trust the authenticity of the piece of paper you received, you have an authentic copy of their public key. Okay, this is kind of easy. So there is, or you can also, you could decide to put your public key or the hash of it in many places. So organizations could decide to print it in a newspaper. This was what originally was conceived. This kind of technique. So if it's between two people, it's kind of easy, right? I mean, the worst case, you just read the hash over the phone. Then the second view or approach was to say, well, how do we distribute public numbers? Well, we did this for a long time in the telephone directory. Those things are now disappearing, but for those of you who are very young, this is this thick book that used to be appearing once in a year in your mailbox, and where you had the phone number of everybody, okay? And so the idea was that you would do the same with public keys, produce a big phone directory with public keys, and then you would authenticate them in a clever way. So you would actually authenticate them all together by hashing them together in a tree shape, and you would only have to authenticate the root value. And this would be in the newspaper, say, or would be in many places. There is just a small problem with this, that if one public key changes, then of course you have to recalculate the whole tree. So a logarithmic number of changes, but a new root value appears. So kind of this never flew because public keys change too quickly, and this kind of authentication trees are not very practical in that sense. So the easiest way to check whether a public key is correct is just ask somebody. I need a public key, or I have a public key, is it correct? You ask, go to a central place and say, is this up to date? Yes or no? In fact, and this is the main mode which we should use today, because we have an online world. In an online world, you just create a central server which has all the public keys. And if you want to know public key, you say, hey, I want to know the public key of this person. Or you have your public key, you can ask, is it still up to date? And you give an answer, yes or no. And today, we actually use this under the name OCSP. And so this is maybe how public keys should work. But the problem is that when public key distribution was invented in 1978, there was no online world. People were offline. And so the models conceived were offline, and the problem is we're still stuck with those even in an online world. So for an offline world, what was conceived was certificates. So this is a concept invented by Kornfelder, and a master student at MIT was working with revest. And so more or less immediately after the invention of RSA, he came up with the idea of a certificate. So, and then about 18 years later, Paul van Oorschot, who actually was so kind to borrow me several slides for his presentation, he actually coined the name public key infrastructure. And the vision behind this that every organization would have an infrastructure, or the e-commerce, or the finance world, or the government world, which distribute public keys. So what is behind this idea is that in a building you have water, electricity, and maybe gas, and also keys. That was more or less the vision behind this. There would be an infrastructure that would give you keys. So unfortunately, we're very far from this in spite of all the ambition and plans. And then if I have time, I will discuss a very cute and weird cryptographic idea, which is due to Shamir. He's a very creative character. And the first practical systems have appeared about 10 years ago, which is identity-based public key cryptography. There the idea is very simple. Your name is your public key. So in fact, this is great, because if your name is your public key, you don't need to distribute public keys anymore. You just need to distribute names. And so, for example, your email address can be your name, and your name is your public key. This is great, because you now solve the problem, right? So it sounds like a cool thing. And when Shamir conceived it in the mid-80s, people thought, if we could only do this. And so about 10, 12 years ago, some Japanese researchers conceived something, and then Dan Bonnet and Mike Reiter had a similar idea or related idea. And so in fact, now there is practical solutions. But the more you think about this, it doesn't work. Okay, so it looks great in practice. It is great to go to a venture capitalist and ask for money and say we have a great idea. But if you start implementing this, you will see it doesn't work. We'll come back to this at the end. So I guess what we all do today is certificates. Who has never heard of certificates? Or nobody dares to confess it, or you've all heard of it. Okay, certificate is like your electronic identity card, which links your public key to your name. That's essentially what it is. It has a distinguished name. This terminology comes from the ITU world. So you should also imagine that, so the ID is 1978, the standards are 1988, or around that time, late 80s. At that time, the telecoms still ruled the world. They had a monopoly in every country, and they had a structure based in Geneva called CCITT, now called ITU, and they ruled the world. So they made decisions, and so the whole public key idea as we have it today is conceived by the telecoms. And so they had a hierarchical view of the world, and so it's kind of a problem because we still suffer from some of the ideas that they had at the time. And for example, terminology and so on is still based on their view of the world, like distinguished names, country names, and so on. Of course, like an identity card, this has a serial number and has a begin and end validity date, and then something which you don't have in an identity card is a link to a revocation list. Because issuing keys is easy, revoking keys is hard. If anybody comes with a great idea how to distribute keys, you always ask the question, and how will you revoke them? And then you will find out whether the method works or not. Because giving out stuff is easy, but revoking stuff is hard. This is more or less essential. Of course, you have a public key there, and you have the name of the CA. So what was the idea conceived to revoke keys? You just have a CRL, so the CA, Certificate Authority, would actually publish every day or every hour a signed list of all revoked certificates. And again, it has a validity date, begin and end, it has a name, and it has a list of revoked certificates. Why doesn't it have the list of public key owners and certificates and public keys? Because for privacy reasons. So you don't want to publish like who has, for example, has left the organization. Most companies don't want to publish a list every day who they fired today. Right? This is something which is typically private. It's also a problem actually of certificates because, in fact, again, most organizations don't want to publish who's working for them with their job titles. So this is also why getting certificates is hard, and getting secure email is hard, because if you want to send an email to, say, somebody working at Siemens or IBM, IBM is not so keen to publish their whole company hierarchy with names and contact information and public keys, because this is private information for the company. And the same for citizens, right? I mean, Belgium cannot publish a list of all their citizens with their email addresses. So this was something which I think the public key world or the telecom world had not conceived, because of course telephone numbers were made public. And so this is what they had in mind, and of course we can't have this in practice. So in terms of cryptography, we've not solved the problem at all because we moved the problem again. Because certificates are signed by the private key of the CA. And so if you want to verify such a signature, you need the public key of the CA. So we moved the problem of secret keys to public keys of users. And now we move one more time the problem of public keys of users to public key of the CA. So now the question is, how do I distribute the public key of the CA? Well, and there is solutions depending on application, but the standard solution today is write it in the browser. Is it secure? No, because any virus can actually update those things. In fact, the different browsers have slightly different lists. And also, as a manager in a company, a security person, it's very hard to control this because users can individually add certificates and remove certificates. So in fact, it's very hard to centrally control. There is also other channels. You could publish it in a newspaper. In Belgium, in the identity cards, the certificate of the CA is also written on your identity card. So it means that actually your identity card has it, and even if there is no access to a browser, you actually have this certificate. Of course, then you don't know whether it's correct, but at least it's another source of the same information, so you can match against the previous value. So I think the important message to remember is this whole thing is very 70s technology-wise, conceived in the 80s, and it sits now everywhere. And this is why it doesn't work very well, because in fact it has a completely different view of the world, and we're now stuck with it. And of course, I'm exaggerating a bit, as I always do, to make the point. Of course, in practice, technology has been adopted to modern technologies and modern ideas, but we still are with leftovers from the past, and this is often a problem. So we look briefly at keys and lifecycle management. At the building blocks of a PKI, we not look at the architecture, how you build it up, but we'll spend more time on trust models. And trust models is actually a way of looking at how multiple CAs can interact. So I will skip this slide because for the interest of time, so essentially what this slide explains is how you can actually secure an email with certificates. Does anybody send secure email here with certificates? 1, 2, 3, using PGP or using certificates really? S-MIME, who uses S-MIME here? 3 people, you see, 4. You see, this is actually the state of the art today. Even the security people don't use it, or 10% of them use it, okay? I think in the general population, it's less than 1%. So as security community, we failed there. There is, of course, usability issues, definitely, but I think there is also other issues, and I think one which is underestimated is the problem of privacy, the fact that in fact, it's hard to get somebody's public key because organizations are not keen to give this out. Okay, so you have to first generate keys, and hopefully you do this properly. As we will see this afternoon or on Friday, it turns out that especially keys generated in embedded devices tend to be not random, and if they're RSA keys, they can be factored easily. The latest news is that the same problem has popped up in the identity cards of Taiwan. And those are produced on common criteria certified cards. Scarier. So even if you have a tested and certified card, it turns out that the keys generated are bad. In case of RSA, it means you can factor them. Then you get a certificate. Okay. Hopefully you use the key, which means there is validation, a regular validation of the key. And then, of course, at some moment the key expires. And a very common practice is just to re-sign the key, and that's it, which is of course not a very good practice. You should refresh the key and generate a new one and start the whole process anew. But so in the industry, a very common practice is if the key expires, they just sign it again, and they continue as if nothing happened. Of course, there is an advantage in changing a key if it ever has been compromised. You actually now can gain new security. You can also use that occasion to increase the key length and so on. So it's not a very good practice to not change your key for every update. And of course, this should all happen in an automated way. You don't want users to see pop-ups and say, please refresh your keys, please enter some random digits, please choose your exponent for RSA. You don't want those things, right? This is the mistakes of the 90s when people were, right, this is cool, we're going to implement public key crypto. Computers are now fast enough for it, but of course, if you make the system unusable or if you ask non-technical people to like generate or choose RSA exponents, then you're really, really bad shape. Okay, but so the vision was behind PKI that you would get an infrastructure where this is all done for you. This is more or less what was the idea. I think this works for individual applications, but the vision was much broader to have unified security. And I think this has failed. This is a vision from the mid-90s, which now today does not work. So the idea was you would have secure email with PKI, but as you've seen, even after, I guess the PKI hype started in the mid-90s, so you see even after 15 years, we're still not there. We don't have secure email, or the use of secure email is still quite marginal. Secure desktop, I guess, yes. Since 2000, every Windows box has its own CA built in. And I'm not saying that our desktops are more secure, but at least we have public key technology in there for code updates and for all kinds of other things. You can use public key technology. Enterprise resource planning, like SAP-like systems and PeopleSoft. KU Leuven is a big user, and I don't think they have any security except for a password. So there, I think it didn't happen. There was no integration whatsoever. You log in and you have access to everything, and nothing is being signed. For VPNs, so for IPsec, we do have public keys, but in small case systems, people prefer to install them manually because it's so complex to do it automatically. But it can be done there. I guess there is large-scale deployments that use it. For the web, there we have millions of certificates issued, and I guess we all use e-commerce on a daily basis or secure access to websites. So there we have a massive usage. But this infrastructure is deeply flawed, in my opinion, but it seems that we don't care, or we don't care enough to really invest in it and to fix the problems. So, but overall, there is no PKI that covers all these things. There is a PKI island for the web. There is email is spotty, desktop, yes, but the vendors do this. I mean, you can be sure that, of course, also the mobile phones have PKI to guarantee updates and guarantee control on your device. VPN is a separate island. ERP, I guess it exists as a product, and some people use it, but it's not massive. Financial sector has, of course, created large PKI. The biggest PKI known is, of course, the EMV, which has, I guess, already more than 1 billion cards issued. So this is the biggest PKI in operation, which is used on a daily basis. And I guess there is more in individual sectors. For example, governments have also rolled out large-scale PKIs. So the central part of PKI is a CA, Certification Authority. So this CA has to create a key pair and a public and a private key. Hopefully this CA also has both a hardware module and a backup. And then hopefully the CA has rented space in a secure building, so a bunker with biometric access, with secure cards for access, with 24/7 guards and dogs and guns, and the whole protection. So because, in fact, I said what we need is an authentic copy of the public key of the CA. We need also something else. We need that the CA keeps its private key private or secret, because if that key leaks out, then you're really in trouble. Okay? And so there is something else we forgot. I will discuss it in the afternoon. Not only, maybe it's the case that this key is in a hardware model, it cannot get out. You also need to make sure that nobody can use this private key in an inappropriate way. That's what we've seen in recent attacks. So the key is in a secure box, but some rogue software or a hacker takes control of the PC talking to this box and then gets things signed. And then there is no point in having your key secure if you can have malware, have anything submitted for signing, right? So in fact, CA needs a secure environment, okay? So there is, of course, a concentration in this industry, and more CAs put all their equipment in central buildings, so to share the cost and to reduce the cost. What is very important is the policy. So if a CA signs certificate, what does it mean? To what is it liable? What has it checked? Of course, how long is a certificate valid? Typically, this is 1 year. Initially, it was 1 year because the CAs wanted an annual revenue. Of course, identity cards and passports, they also have CAs, and they typically have 5 or 10 year validity. Which algorithms can be used, which key lines, which are all the rules that control stuff. So in general, you get quite a long policy. And so it essentially says for what the CA is liable. And I'm not a lawyer, but if you read those policies, They're very long, and they say they're not liable for anything. That's mostly what most policies say, right? And it's kind of amazing. I think we have the problem less in Europe, but in particular in the Anglo-Saxon world, the concept of identity there is very different from here. So here, this is something we can thank Napoleon for. Napoleon needed soldiers for his big wars. So everybody would choose a name. He made a public register so he could find the soldiers. And changing your name was kind of against the constitution. So it's very difficult in most of Europe, except for the Anglo-Saxon world, to change your name. While in the UK and the US, you can just change your name like this. I think the only exception is if you're in a lawsuit, you actually can't do it for a while because the judge may be confused. But for the rest, you can change your name every other week if you really feel like this. And so in those kind of worlds, of course, this is very difficult to check something. So if you move to the UK, you'll find out that if you want to open a bank account, they will ask for your gas bill and electricity bill to identify you, because they don't have an identity card and a government register. And so you can see that the CA in the Anglo-Saxon world, if it has to check identity, well, it has to use gas bills or electricity bills. And this is painful, so they'll typically just believe you, right? So there is a big problem there. Of course, in the banking world, banks do know their clients. And of course, the government, especially in the non-Anglo-Saxon world, also knows who people are. But even there, we've seen fraud cases with a Belgian guy who happened to have 3 identity cards, right? So those things happen. But at least it depends on the different culture. But in the Anglo-Saxon world, checking who somebody is actually quite much harder than it is, I would say, in Belgium, in France, or in Germany. Then, of course, you need to store these certificates in a database, a repository. And I forgot to mention this, but so the standard for this repository was X500, the directory. So X500 was supposed to be the directory like the electronic telephone book. And the mail program was X400. I guess there is not many people who still have used X400 mails in the 80s. There were very interesting mails that those who didn't arrive. Well, usually it didn't work, X400. And if it worked, you were really happy. And all the messages were very, very long because there were a lot of headers inserted that nobody understood and nobody could deal with. But so this is what the telecoms did. So they made a mail program X400, which, or a mail interface, which unfortunately disappeared, or fortunately disappeared. And X500 was a directory, and X509 was a certificate standard. So this standard which specifies how a certificate should look. This is the X509 standard. And so the access to the database was X500 and was also horrible. So after a while, the industry got rid of it, and they created LDAP. LDAP stands for Lightweight Directory Access Protocol. So it was lightweight because X500 was heavyweight. Okay, so it was kind of, they got fed up with X500 and they made something simpler. So I'm not at all an expert in databases. But what I know for sure is that there is even less standardization than in CAs. So, of course, as a naive academic or as a naive young person, you may think that you create CA standards and certificate standards, and you make sure that everybody can understand everybody else's certificates. Okay? There is interoperability. Now, of course, the CA industry, this is kind of the gold rush of the 90s. So some people got very, very rich. In Baltimore is a famous example, in Ireland. But there is also Mark Shuttleworth from Taute. So he used his money to go on the space shuttle, right? So it was kind of a gold rush. And the model was to make sure that you would lock in your customers. So you would define certificates that could not be understood by anybody else. And for this purpose, X509 got extensions. And so every vendor had its own extensions. And so, in fact, so they made sure that if you had a certificate from vendor A, it could not be understood by software from vendor B and vice versa. So they tried to lock in their clients, and so it was very difficult to actually change vendors. Or it was difficult to have multiple vendors supplying you PKI infrastructure. So apparently, the database experts told me that for databases it was even worse. So, and when did this problem happen? So in the mid-90s, if you were a large company, you had to have at least 10 CA projects, 10 PKIs, or you were not really doing well. And then, of course, we also got .com hype and a lot of mergers. And then when people started to merging two companies, they realized that the databases were completely incompatible. And so same for certificates and whatever. So it was really a very inefficient world. And so then it led to a very large concentration on the one hand. And in terms of security, it led to a race to the bottom, to be cheaper and less secure. And then you got a bigger market share, and you could actually win. That was more or less what happened. So not a very nice story from a security point of view, I would say. And of course, as I mentioned, these databases are not public. So they can be used internally, but you cannot send secure email based on these directories to other companies because they don't want to open up the directory to you. And revocation. So all these systems, of course, boil down to revocation. If you look at the key management infrastructure or products of a vendor or a solution, you always ask, what about revocation? Okay. And so for all the flaws of the financial systems, and I guess Stephen will tell you about the flaws he found in EMV, one thing that the financial sector knows how to do is revoke stuff, right? They even revoke things when you don't want it, as you probably have experienced already, but they're very good at this, okay? So there is a number that you can call, and immediately everything is revoked. This is something they know how to do very well. So certificates are like identity cards, and they were designed to be offline. So if somebody shows you a certificate and tries to log in, for example, to get a service, the question which you have as relying party is the certificate still valid? Has it not been revoked? But if you really want to know the latest information, you have to go online, right? Because if it was revoked 1 minute ago, how would you be able to know? Only by going online. Of course, this was not feasible initially. It was too expensive. So what they did was CRLs, and the idea was that in the morning you would download a blacklist and you would check whether the certificate was on this blacklist. It was quite similar to what happened in the shops in the 80s with the bank cards. They had lists of withdrawn credit cards. In fact, they were hanging up there as small lists, and of course, if this got too big, it became books. In the end, they had to move to an online system. So something similar happens. So if, in fact, a web browser accepts a certificate, say, or your browser accepts a certificate of a server, you should actually download the CRL every morning and then check whether this server certificate is revoked or not. Now, you should again move back to the 90s, mid-90s, and people did not have 10 megabit ADSL lines, right? People had still kilobit modems, 56 kilobit modems. So downloading a CRL of a few megabytes, people just didn't do it. So how was this discovered? Well, even in 2001, I believe, VeriSign, a big operator, signed 2 Microsoft developer keys, which were actually not Microsoft developer keys. So they could now be used to inject fake Microsoft software into the system. Apparently, the guy at VeriSign was fired because he didn't check properly that these were really Microsoft employees. So what was the problem? Well, very simple. VeriSign has to revoke those 2 certificates, right? They did that. And then they found out that nobody checked revocation lists. So IE, even Explorer, did not check revocation lists. They were in the standards, but they didn't bother to check them. Why would you do this? It slows down the browsing experience. Okay? So then there was a quick patch to IE to actually implement this revocation mechanism. So it should actually be done in a transparent way. And of course, ideally, you want to do it online. And this is what we do today. I'll come back to this. It still doesn't work. So you can think about what happens. So your browser gets a certificate, say, from Microsoft, and then it will now contact a server and ask whether the certificate is still valid or not. Okay? And there is 3 possibilities. You give an answer back, yes, it's okay. You give an answer back, no, it's not okay. And 3, there is no answer. Now, I'll let you guess what happens if there is no answer. Think about it. I'll tell you the answer later. But it's not good. So keys should be updated automatically. So users should not know about this when keys are updated. Ideally, it should all be transparent. And especially if you use certificates to encrypt information, then update is very critical, because if somehow a key update happens and something goes wrong, then you lose access to all your information. This is also the reason why in Belgium it was decided to issue 2 keys to every card. In fact, there is 3 keys. There is a card management key without certificate, but the government has a database of this. There is an authentication key to log into websites, and there is a signing key to digitally sign documents. And you would think, naturally, you also have an encryption-decryption key pair to decrypt messages. But I think the government, and we thought it was too risky, because if actually somebody encrypts all his files with this key, and then puts this card in his shirt, and the shirt in the washing machine, then all the keys are gone. And then also all the data is gone. And then they may come after the government, right? And say, what did you do? You created damage. So if you want to use key pairs for encryption and decryption of data, you should have a backup somewhere, right? And the government did not want to provide a backup, because if they would offer you a backup, then they would always say people are spying on us and the government wants our keys. But at least in a company, you want a backup. Well, because the data is owned by the company. And anyway, if the employee botches the thing, he loses his password, he damages the card or whatever, something goes wrong, you want to be able to recover the data. Okay. But so in general, it's quite painful. And in Belgium, I know as a citizen, you can actually apply for new certificates for your existing card, but I don't know anybody who's ever done it except maybe some people in our group to test the procedure. But ideally, it should be transparent to the user. If the user has to do something, forget it. So you're security experts, you know what certificates are and public keys, but you can't expect that the average person in the street understands this. And of course, you place the key, not the expiration date. So the other interesting thing related to key update, but also revocation, is what about CA keys? Well, for example, the CA keys, when they were issued initially, say 95, 97, they put an expiration date of 2005. This was 10 years in the future. By that, all the people who founded the company were already sitting on a tropical island, and they didn't worry about it. But of course, in 2005, those people who were working at these CAs said, now we have a problem. Our CA key has to be updated. How do we do this? Okay. Or always, also in the beginning of the CA year, so today all these always are done by the big 5 or big 4 consulting companies. But in the mid-90s, these companies didn't even know what PKI was. So they did this always with me, and I always asked the question to the CA, and what will happen if your private key is compromised? And the only answer I ever got was silence. This will never happen. That's what they said. So I even know a case, and I cannot give the details, of a large bank where there was this big signing ceremony. The signing ceremony, then the keys are generated, and there is a whole process being described. There is a whole algorithm and procedure, and the openers come in, and the CEO of the company comes in, and then the security officer generates the keys and makes a backup on this and whatever. So there is a whole, and then everybody signs off for it. And so what happened at a large bank was that the security guy actually made a backup copy of the private key of a CA and put it in his pocket. And then later on, when they cut his budget, he blackmailed his CEO with this. It was very stupid, and he was fired, actually. But it just shows you that you have all these consultants and all these big guys coming in and saying, look, we're going to check that everything is secure. And while they're watching, this guy just makes a backup copy, right? Because who understands what's really happening? No one, except for the security people. So it's actually a very interesting lesson to remember. And so if you want to blackmail your company, don't do it while you're still working for them. That's not a very good strategy to become rich, right? Find some better attack, okay? Okay, so key backup and recovery, we already discussed this briefly. So you really want backup of keys, right? Because if you don't have a backup and your keys somehow die, the HSM dies, the smart card dies, or users forget their password and can't, this is for a software-based system, then you lose all your data. Or people leave, or they're requested to leave, or they leave by themselves spontaneously, or maybe a bad accident happens. So in all these cases, you want access to backup information. Okay? So, of course, this is only for signing, for encryption and decryption keys. For signing keys, you should really think twice whether you want the backup or not. And under influence of the Germans, who are very rigid in security, in fact, the European Signature Directive does not allow you to make a backup copy of signing keys. Why not? Because if there is a backup copy, in fact, you could afterwards say, well, I didn't sign, somebody took the backup and signed in my name. So I'm not sure whether I want to go into full detail of the whole story, but essentially in the 90s, so the early 90s, government still tried to control crypto. So the 80s policy was, you should not know about crypto. You should not have crypto as citizens, and if you have crypto, we give you a weak one, like the GSM phones. And then in the early 90s, when it became clear that it was impossible to control crypto because people were publishing crypto books and people were downloading crypto software from everywhere. So then the idea of the government was, let's control the keys. And so the Clipper chip was designed at the time. The Clipper chip was the response to AT&T. So AT&T was bringing out a secure phone with triple-dash encryption. it was oriented towards business users, not government users, but business users. And of course, then the US government started panicking because that would mean that they would lose access to eavesdrop phones. And so then they proposed an alternative called Clipper, and Clipper was encryption for phones and for PCs for data, but the idea would be that the government has a backup of your key. And so the US government was pushing this, and they were telling companies, look, if you implement a backup copy, we're happy to actually keep backup copies of all your keys. So in fact, if there is a problem, we can always help you. And essentially, they were nudging companies to accept this by saying, if you give us backup copies, you're allowed to export crypto. Because it was impossible to control the use of crypto, but exporting crypto was still illegal. And in fact, this story ended in 99 or 2000. Finally, inside Europe, but also between Europe and the US, it became possible to export crypto. But when we did projects in the 90s, when we wrote software, we gave it to somebody of Siemens, and he integrated it in a library, then the guy from Siemens applied for an export permission to actually give us back the software. Or I also know that we had to give with this project a demonstration in the north of Italy at the Garda Lake, and the PCs were coming from Siemens, and Siemens tried to get an import and export permission from Switzerland to drive from Munich to the Garda Lake. They never could get it, so they had to go through Austria. So this is 98. This is not 20 decades ago or something, or this is not mid-20th. This is only 15 years ago. So in the end, the US government had to give up on these controls. But in fact, to try to nudge people into key escrow, they actually said, if you give us key escrow or if you give us the key, then you can export your stuff. So one of the reasons why they had to abandon this was because that the Randall algorithm designed in Belgium actually won the AES competition. If they wouldn't have changed the laws, if the two winners would have gone to the US with AES on their laptop and flown out again, they could have been arrested for export violations, right? Because they would take their own algorithm back home. And so that was so ridiculous that they probably realized that they had to do something about this. Okay. So there is two things here. Well, government want access to communication keys because they're used to eavesdropping communications. As a company, you don't need backup communication keys. Most companies don't eavesdrop on their staff communications, and if they need to, they can do it at the endpoints. While, of course, the key escrow of the backup company, the backup problem for companies is for stored information. And there, the government doesn't need your keys at all. So this is, by confusing these two matters, communication and storage, the government tried to create some incentives. And so as a response, the EU Signature Directive said you can't regulate CAs. This was a very important move, which is maybe now hard to understand. But so the government tried to control crypto to CAs. And the directive of the EU said you can't regulate, or you can't forbid somebody to operate a CA. So you can't force them to give the government copies of keys. That's one thing. And on the other hand, they say you're not allowed to take backup copies of signing keys. Now, I think this is pretty stupid because I can imagine that, for example, if you look at large companies, they need, of course, redundancy, and you would like to use the same key in multiple servers. Also, important CAs from large financial institutions, of course, I mean, the Visa public key is in 10 million terminals. You really think that they don't have a backup copy of their private key, and if something happens to this machine, that they're going to put a new public key in 10 million terminals? Of course not. And in fact, you can do much better. You can do threshold crypto. In threshold crypto, you have a key, you split it in 5 pieces, and you store this in 5 servers. And if 3 servers work, you can reconstruct the key and sign stuff. And it's also more secure because if you compromise 1 or 2 servers, you can't even sign anything. So this is actually a much better mechanism to do stuff.
What's the name of that?
Threshold cryptography. So it has been deployed. It's technology which is date back to the crypto research of the mid-90s. It was first deployed by Certco, who actually, I think, sold it to Visa. I don't know what happened to Certco, the company, probably been absorbed by somebody. And I think it's public that Swift uses this, for example, for their CA. So they have actually their key goes to notary publics. So I don't know, I can't reveal how many shares, but they have shares with notary publics and directors of the company. And so even if somebody is in vacation and a notary public has passed away, they can still reconstruct the key. So it's an example of great crypto technology which is not widely used and which could have stopped many attacks. Okay, so then non-repudiation. So initially, the practice was to, for efficiency reasons and for simplicity reasons, to use the same key pair for encryption and signatures, which is, of course, a problem in the sense that you want the backup of your decryption keys, but not ideally not of the signing keys. Or you can argue about this. At least it should be different ways of backing things up. The signing key, the backup should be made by the signer. For the decryption key, you can argue the backup should be made by the organization so that they can access the information in case they need to. Okay? So you want independent life cycles. I mean, decryption keys, ideally you would like to be able to decrypt in the future if you have data which you stored today, right? Even if the key has expired, you may still want to decrypt. You could, of course, re-encrypt everything, but this is kind of painful. For signing keys, if they expire, you will definitely destroy the signing key afterwards. You can still verify signatures, but not sign. Yes, Jim?
I'm just, sorry, I'm ignorant of this. I don't understand why we don't want backup for signature private keys. Can you give me that one more time?
Well, essentially, I mean, I'm also in two minds of this. I would prefer to have a backup of my signing key. But essentially, I think the reason for this is that in Europe, we try to prevent control of use of crypto and to the CAs. Okay, so there was this kind of the UK, typically in France, they said, we're going to control use of crypto by controlling CAs. And so if CAs want to be in business, they have to get a license from the state. That was the vision of their states. And in fact, every time they issue a key pair, they have to keep a copy of the private key and give it to the government. Okay? And of course, this is for decryption keys. But initially, especially in the 90s, most companies had just one key pair. Okay? And so the other argument, so this is one thing. So and of course, if the government has a copy of your signing key, you can always say they frame you. The same thing in your organization, right? I mean, you sign an important transaction which you shouldn't have signed. And then you're called by the manager, and you say, well, you know, the system manager has done this in my name because he has actually a database with the backup keys. I think my argument or my viewpoint is, as a signing key, you should have your own backup. Because if I put my identity card in a washing machine, ideally, I would like to actually have a backup and get a new identity card with the same signing keys. So the outside world should not see my signing keys have changed. My signature should remain the same. But it's a difficult question. Yeah, it's coming up. It's coming up. There's quite some work on this, and also this afternoon or on Friday I will talk about this. So in the end, I think Europe did a good thing here by saying you can't license CAs. And so in fact, we do have a much more free regime, so the control of crypto to CAs never happened. This is a good thing of Europe, which actually most people don't realize. We discussed already, you have different policies for every key pair. So now the big problem is cross-certification. So as I said, everybody tried to grab market share. And even a company like Siemens, they probably had more than 10 CA projects at the same time in the late 90s. Because the finance division was doing its own CA pair, the engineering division, probably the power division. If you wanted to be cool, you had to have a CA. It's like today, if you want to be cool, you have to have an app for something in your company. Today, at that time, you had to have a CA. And of course, the problem is now what to do if there is more than one CA. So of course, if it's peer-to-peer, it's kind of clear. Then one signs the other. You sign each other public keys, and you have a cross relationship. Okay? But in the financial world, it's very different. You have a hierarchy. And so we'll come back to this in more detail. I'll skip it here, but I just want to point out already the problem that the whole thing was conceived, of course, by CCITT to have only one CA in Geneva, and they would sign all the national telecoms, and they would sign all the companies. So that was, and then the users. That was the vision, to have a three-level hierarchy, and this is how the world would work. It would be a nice source of revenue, and a great way to control the world. So maybe I can already make one comment. So every certificate has, of course, certificate policy. Every CA has a certificate practice statement, also has policies, which essentially say what they do to check a certificate, what they do to check for revocation, what they do if a certificate is revoked, and so on. So, of course, as an engineer, you can now immediately see the next paper you will write, but I have to disappoint you, it has already been written. If you have a graph of CAs, which have signed each other's public keys, you have two users, which are subscribed to or certified by random CAs, is there a trust path in between the two? Can they trust each other's public keys? So you have to find actually a path in a directed graph, and then the question is, what if there is more than one path? Should you take the shortest path? Should you combine the path? You can see all the papers that have been written, right? Now this is all engineering, this is great, but now you forgot the lawyers. Because every CA that signs something comes with 80 pages of legalese, what it means. So now if you take a path, so a CA signs a key of a public key of a user, which is 80 pages of legalese. It signs a key of another CA, with 80 pages of legalese. And this CA signs a key of a user with 80 pages of legalese. Now you get 240 pages of legalese. What does it mean? Well, you then hire 10 lawyers, you put them in a room, and you get 17 answers, right? Nobody knows what it means. If you concatenate 240 pages of legalese, what does it mean? And this is where the whole thing goes wrong. It's not in the finding a path in a graph. It's actually what does it mean in practice, and who will pay when something goes wrong. And they all say, I'm not going to pay. Timestamping, this is also very interesting because everybody agrees for a long time that you need timestamping. I will argue why. But in fact, in practice, it's only rarely implemented, even today. I think there are CAs that have it, and I think if you went to the RSA conference, say 6, 7, 8 years ago, there were several timestamping companies selling servers, but today they're all gone. So I hope that this means that everybody now has timestamping servers in their own offering. I don't know. So of course, you need to do this legally, because for many legal reasons, you need to be able to prove when something happened. For example, in patent disputes, when you filed a patent or when you did the research, or if you file documents and so on. So also business transactions, you have to be able to fix them in time, if only for accounting, right? Did the transaction happen in 2012 or 2013? So this is definitely important. But it also is important for revocation, because essentially you have to look at two scenarios. Scenario one, I sign a document which is legally binding and which kind of implicates my company in a serious way. And one day later, I discover that my private key is compromised. Right? I detect a virus on my machine to which I had a smart card inserted, and so I now have a real problem. So I will revoke my signing key. But it's clear, but if I sign something yesterday and I revoke my key today, the signature of yesterday is still valid. Okay. On the other hand, of course, if my key is compromised yesterday, and today a signature of me shows up, clearly this signature is not valid, because at least not if I contact the CA and say, hey, stop approving my key, put my key in the revocation list. So actually nobody should actually accept my key as valid, right? So, but this only works. So how can you distinguish the two cases? In one case, first signing, then revocation. The other one, first revocation, then signing. You can only do this when you know who has when you signed. Okay? Now you can say, oh, I have a solution, because as a signer, I will insert a time in every signature. Does this work? You're even more asleep than I am, it seems. It doesn't work, because, of course, if I have the signing key of somebody, I will put an old date in there in the signature. I will say the signature of last month when the key was still valid. So it doesn't protect you, because if I put a date in, as an attacker, I put an old date in there when the key was valid. So you can only really have non-repudiation or binding signatures when every signature is certified in time by an external party. So you have to have an external log or an external timestamping service that says this signature existed at a certain time. This is kind of obvious once you think about it, but still CAs may offer all services without offering timestamping services. Okay. So initially, there was also a major problem, because the whole PKI hype happened in the late 90s, say between 96 and 99. But in fact, at that moment, the PKI companies were ready to give you software to generate public keys and for certificates, and all the standards were being written. But the applications would not be able to deal with public keys. So the SAPs, the email programs, the desktop software, the OSs would not be able to deal with it. So it took a very long time to actually adjust all the application software, and it's still not being done. And it's also very hard to do it because of this arcane standard and all these complex formats, and because everybody has different certificates and so on. So in fact, because certificates are extensible, this is great as a flexible business tool, But in fact, from an implementation point of view, if you want to verify certificates, it's a nightmare. And I think it's still popping up today that a lot of certificate verification software is buggy and wrong. So if you take average certificate certification software, it will actually not work, or will make serious mistakes and accept certificates that it should not accept. So this vision is very nice, but so it's a beautiful slide made by Paul van Oorschot and his marketing people in 1996, but that's not how the world works. So forget about this. So I guess if you look at all these things, you already see that PKI is complex. So although the principles are very simple, I can explain to you in 2 or 3 slides what it is. If you want to detail everything and all the interfaces and so on, and then you realize that everybody had different options. So if you go to PKIX, the IETF group with standards, you will find there dozens of RFCs and probably more than 1,000 pages of standards. And so the code to actually generate certificates, verify certificates, check timestamping and whatever, is all quite complex. Okay? I mean, it's not helped by the fact that X509 certificates we still use is based on ASN1, which apparently people can't write decent code for. Okay? It's always buggy and there is many problems. So in principle, it's simple. In practice, it's complex. So if you want to look at the standards, so of course the original standards are hard to get because they're X509 standards, so the CCITD, which are not on the internet, but of course they became ISO standards, and then they were profiled, so specialized in IETF. And so that work is the work I think used by the industry mostly. So there is certificates, CRL profiles, certificate management protocols, and there is a whole roadmap even describing you how all the documents stick together. But there is lots of documents and lots of options. It's incredibly complex once you start looking at the details. This I will skip. So interesting question is also key generation. So where do you generate keys? I guess after the recent incidents of about a year ago, we know that you should not generate them in embedded devices because they actually don't have enough entropy. So the problem with these embedded devices, these routers and so on, and the access points, they boot up. There is no user interaction. And in fact, unless you add a special hardware random number generator, they actually generate a small set of public keys, which can be easily broken. So it's actually pretty tricky to make good software. And ideally, you want hardware support. And so my advice would have been use a smart card, because it's a physically protected environment, and there is random number generators in there which have been certified, or a hardware security module. Now, after the Taiwan story, I'm not so sure about smart cards anymore. And as soon as I saw the attack, so this is about 1 year and 1 month ago, we sent a formal request to the Belgian government to ask to get all the public keys so we can check whether they're vulnerable or not. We still haven't received the public keys. So the Belgian government prefers to stick their head in the sand and say, if nobody has the public keys, then we can't know whether they actually are vulnerable or not. So this is what their approach is. Anyway, but so the initial idea which was pushed by governments is key generation is hard. Let the CAs do it for you so they can actually give us a copy of the private key. This was more or less the philosophy. Right? It's hard, so we can generate your keys. This is fine. So then, of course, you end up with a problem because that means that there is a CA based in Geneva or in Belgium, say in Brussels, which has all the private keys. And how do you get the keys to the users? Now you get a big key management problem. Okay, because you can't send them encrypted under a password over the internet, right? So I'm not a big fan of this. You can say let the user do it, but then of course, what will the user do, right? Will he first put his identity card in a microwave oven for 10 minutes and then see what kind of keys come out? So it's also not ideal. So you can also say we outsource this. So the solution we've chosen for the Belgian ID card, I'm not saying it's perfect, but I think it is kind of a compromise, is that the keys are generated on the card while the card is in control of the card manufacturer. But it's not the producer of the chip, not the entity who loads the operating system. It's when the card is produced. In fact, the chip is produced, it's inserted in the card, the plastic card by ZTES, and at that moment, there is a command issued, generate key pair. And we've checked the software. There seems to be no command to extract the secret key from the card, or the private key. We can only extract the public key. This public key is then sent to the government, who sends it to Global Sign for signing, and then the certificate goes back to the card. So this is kind of a compromise solution. the key is generated while the card is in the hands of a private company, but the private key should never come out. So the key is generated on the card. So this is kind of one way of doing it. But if you want backup copies, you have to do it yourself, obviously. So now comes the more interesting part, is trust models. So how do we actually integrate CAs with the real world? So the CCITT view of the world was very simple. We are in charge, so we'll control the world, we control the keys, and everything is great. Of course, it turns out that there is now competition and that the telecoms are not the only powerful players. We have some players like the banks who are very powerful. The governments are in the market. There is some small companies like Google and Apple and so on. They seem to have quite some power over us as well. So it's quite unclear what's happening. But the initial model was very simple. There will be a CCITT or ITU label. They will have the root CA in Geneva. You will all trust them because you have to trust them, because you trust your telecom, because they're good. Okay, this was more or less the idea. And so you will all trust them. This is the dotted arrow up. And so in exchange, they will sign your public keys. Okay, so of course, this was kind of an inconvenient model, because if every citizen in the world or every company has to go to Geneva to get the public key signed, this is kind of impractical. So they came up with a slightly better model where the root CA would be in Geneva and every country would have its national CA. It's called subordinate CAs. But as a citizen, you would still, and so what you do is, as a root CA, you sign the public key of a subordinate CA. As a subordinate CA, you sign the public key of the company or the user, but the user still trusts CCITT or ITU. So you would still trust the Geneva guys to set the policies. So all the rules are made in Geneva, and you as a user get a card with a logo, and this logo would say CCITT or today ITU. That was the vision. Do we have this model today? Anywhere? Yes, we have this model. Visa and MasterCard. If you get a Visa card or a MasterCard with a PKI, it has a Visa or MasterCard logo. And Visa or MasterCard, they have a CA, and they sign the bank keys, and the bank signed your keys. But the bank cannot just operate its own CA and decide what they do. In fact, Visa specifies exactly what they should do to issue cards, what should be in a certificate. The real boss is Visa, it's not the bank. Okay? So I guess the registration procedure can be bank dependent, but in the end, the bank is liable if they make a mistake. If they give Visa cards to the wrong people, then they're liable. But the rules are set by Visa. Which kind of audit has to happen, which kind of certificate format, and so on. So the rules set by Visa, and you as a user, you trust the Visa logo, or the merchant trusts the Visa logo. So you may go to Australia where nobody has heard of KBC, but because they see the Visa logo, the relying party trusts your card. Of course, in companies, it doesn't work like this, in the sense that, say, you have, for example, Microsoft and Apple, and Microsoft has its own CA, and the Microsoft employees trust the Microsoft logo and brand and CA, and the Apple employees trust the Apple brand or logo. So, and you get locally signed certificates. So this is fine as long as there is no interaction. But so assume that Microsoft would decide to put Office on the iPad. At some moment, they will have to talk, right? So at that moment, maybe it's decided that Microsoft will sign the Apple public key and Apple will sign the Microsoft public key. And so now somebody from the team in Microsoft to port Office to the iPad can now talk to somebody in Apple from the team that deals with Office for the iPad and the interfaces. And so there actually now is a trust path and everything works. Except for the small detail which I told you, which is the legalese. Okay, so technology-wise, it's quite simple. So A just checks two certificates, the signature of CA, the Microsoft CA on the CA of Apple, and the signature of the Apple CA on the public key of the Apple employee B. So this is technically easy. Of course, the legalese is something else. What does it mean? What if something goes wrong? What about revocation? And so on and so on. This is going to be complex. Of course, the world can be more complex. And I think a typical example there is the pharmaceutical industry or also the automobile industry. So what happens there, of course, is you have a few big players. Say in the US, you have the big three. But then, of course, there is hundreds of supplying companies. And so, you know, maybe Ford and General Motors decide to collaborate for something, so they sign each other public keys. And then it turns out that there is a supplier of General Motors that actually is certified by General Motors. And then for some reason, the supplier certifies the public key of Ford. And so you actually created a very complex network with hundreds of companies which each had their own CA and signing each other public keys. And so this is actually how business develops. There is no hierarchy. There is no single authority that can say in the automobile business, we're the boss. If you want to be in our business, we will sign your public key. It doesn't work because just Ford, General Motors, and Chrysler, they can't accept one authority, right? They're competitors, and they typically don't want to create a neutral authority that sets the rules for everybody. So for the users, you still trust only your local CA. You don't trust any of the others, okay? So, of course, after a while, it becomes unworkable, and so then the so-called hub and spoke model was invented. So this, I think, originated in ANX, the Automobile Exchange Network, and I believe the pharmaceutical industry has the same model. So there, you create kind of a central party which everybody certifies. Okay? So everybody signs a public key of the central party, which is the hub. The central party signs the public key of every player. But there is no hierarchy. You may agree on formats and you may agree on stuff, but in the end, it's a mutual agreement. And what is very important is the users still only trust their own CA. Okay, the users don't know about this hub. This hub is not the boss. This hub does not set the rules. Okay. This is for business to business, has worked quite well. And then now the browser model. So in the browser model, as we discussed, how does CA distribute this public key today? So at least for those who certify websites, it's very simple. You go to Mozilla, Microsoft, Apple, and the likes, and you ask them to put your public key in the browser. So now, the browser will actually sign the public key of the server. So if you have an e-commerce server, so tomorrow you're going to start your business selling security gadgets, and you want to actually do this electronically, well, then you have to create your own CA, your own server. What's a CA? A server you have to create with a key pair, and you go with your public key. You can choose to who you go. Maybe you go to GlobalSign, or you go to VeriSign, or to Tholte, or any of the 65 others, and you ask them to sign your public key. Okay. So as a user, if you use your browser, in fact, you trust all these signing authorities. And a typical browser has about 600, although the industry says there is only 65, because some of them are kind of related to each other. So there is, what the industry numbers I heard last week is there is about 65 CAs that actually do issue certificates and that have their own kind of worlds. But they may have different sub-CAs. So as a user, if you go to a website and with your browser the lock closes, you now have secure communication. So a Diffie-Hellman protocol or RSA protocol has been run. This relies on the public key of the server, which has been used. And this public key of a server has been certified by somebody. Who? You don't know. In fact, the only thing your browser tells you is the public key of this server has been signed by one of the CAs in the browser. Who has already looked at those CAs? Nobody. One person? I mean, I'm not going to do this because I have to interrupt the presentation, but we can do it before lunch. You should do this. It's quite tricky because I keep forgetting how to get there, and the browsers keep changing it to make sure it's hard to get there. But if you go there, you will find hundreds of names, and you will actually find out that you trust, of course, VeriSign and Tholte, and Baltimore is still in there, although the company is under for several years. I don't know who bought their keys. I should still find out. Maybe the mafia. But the German government is in there, the Turkish government, the Chinese government. There is even a company known to be owned by the CA, which is in there to spoof connections. So in fact, if you use your browser and you don't edit those certificates, you trust all those CAs. And if you really want, you can figure out who signed this certificate, but if you just use a browser, you don't find out, and you trust anybody. So in fact, you trust, as a user, this whole universum, where there is actually not much check. Okay? So, Pete, yes?
It's difficult to get into that list.
It's claimed to be difficult to get into, but the CIA seems to be able to get in there. So it can't be that difficult. You just need some money.
But look, for instance, CSRT, so an open source
Yes.
initiative or community effort to get into there, they're trying over
Yes.
10 years to get into there.
Yeah.
So
But of course,
controlled by the browser.
yeah, so there is a forum, I heard about it last week, the CIA Browser Forum, which sets all these rules and polices this. And they say that everything is fine, there is no problem. Of course, if you do an open CA and you say, I'm not going to charge for certificates, you're undermining their business model, so they will try to stop you, right? The ecosystem is not designed to create security, it's designed to make money, right? This is something very important to understand, that the whole CA and SSL mechanism is designed to make some people very rich. I don't think these companies made a lot of money, but at least what happened is that the founders made a lot of money because some people believed they would be making more money. That was essentially what happened. But so, of course, there is some controls. You can't just enter there. You have to pay some money, and you have to undergo some audit, and there's some rules. But as we found out, these rules are quite fake. It's more like about dealing with money and promising not to undermine the business model. In fact, sometimes you can see it as a cartel. Okay? So the EFF, Electronic Frontier Foundation in the US, has a very bright guy, Peter Eckersley, and we decided to do a study of the SSL-verse 3 years ago. It's a very interesting paper. And so he scanned the whole internet, and he found about 11 million servers that start an SSL handshake, and about half of them has a valid certificate chain. Okay? So by the way, for example, in my group, it may well be we set up a server for say, a conference, and we don't even bother to ask for certificates. So if you then go to the server, you get a pop-up saying this key is untrusted. But if it's really only for a conference review, who cares? Why should we actually go to all the pain? I mean, so this is if your users are experts, because we're security people anyway, for security conference, you can deal with this. But if you don't have your key signed, then you get a pop-up, which says this server key is untrusted, you want to accept it. And I think browsers have made it harder than in the past to go past this. In the past, it was one click, now you have to click several times to go past an untrusted key. Yes?
I think they're doing a better job, especially Firefox. I think they're actually doing a
Yes.
pretty responsible job at it.
Definitely. So Peter Eckersley found 650 CA certs trustable by Windows or Firefox. Now, what the CA Browser Forum said last week is, well, in fact, there is only 65 real ones, and the other ones are sub-CAs. So everyone has about 10 sub-CAs. So there is only 65 players, okay? Which includes, of course, many governments, about 24 governments. So there is 1.4 unique leaf certs. For example, 300,000 leaf certs are signed by one GoDaddy cert. So if that ever gets compromised, then 300,000 servers have to change their key or have to do something. This is really kind of a concentration which is not optimal. And it's a consequence of the race to the bottom. So I presume that GoDaddy has been the cheapest, so everybody goes there, right?
And they're very poor for the CRL.
Of course.
So they cannot respond to
You have to save money, right, Jim?
Yeah, but back up, I didn't follow. You said 650 C search trustable by Windows or Firefox, but industry only 65 million.
That's what they say last week. I didn't have time to investigate the claim, but it's, for example, it is true that, for example, VeriSign has like many keys in there. And so they claim also that, I don't know the exact details, right? I didn't have time to do my research, but I can see that, for example, it may well be that Turk Trust is not the case, but it could be that Turk Trust is a subcontractor of GlobalSign, right? The Turkish government decides not to put their own CA out, but actually goes to GlobalSign, and then Turk Trust will be separately in your browser, but in fact, Turk Trust thing is under GlobalSign control. So I think they probably have 65 members who claim to control all or present all those CAs. That's, I think, how you can read their statement. It makes no difference for me whether it's 65 or 650, right? I only want to trust maybe 5 as a person. I can probably check 5 organizations, 65, 650. I just want to give you their response because I find it interesting that they respond to this, right? This is their response. It's only 65. So 80 distinct keys are used in multiple CA certs. There is several CAs that sign the IP address 192.168.1.2. I hope you see the humor of this. It's actually not funny. You should never sign such an IP address. It just shows you that people are plainly incompetent or careless. There is 2 leaf certs that still have 508-bit keys. This can be factored today in a couple of hours. Okay. And of course, in 2006, what happened is that some not-so-smart person looked at the Debian OpenSSL code and he found the randomness used to generate RSA keys, and he found this very weird that calls were made to strange things, and so he commented all of this out. And as a consequence, all the keys generated by this particular OpenSSL version belong to a very small set of 28,000. And anybody of you can go get this code, run it, and get all those keys, the public keys and the private keys. Okay? And so this actually, this software version was in use for about 3 weeks. So fortunately, only 530 of those at this moment validate, but only 73 have been revoked. So you would think that as a responsible industry, something like this happens, you immediately, the next day, you issue a CRL for 28,000 public keys that can never be accepted anywhere. But they didn't do this. They only revoke one if you ask for it explicitly. And I happen to know one organization which was a victim where I'm involved, and we actually got the revocation, but it was really painful. So it just shows they're interested in making money, but not in really caring about security, right? So how to fix this mess? So the CA Browser Forum guy gave a talk last week at the beginning of a panel, and he said, in fact, we have quite some incidents, and I will come back to this, but we didn't do it so badly. It's actually not so bad, because every year we issue 2 million certificates, and in total, only about 1,000 are fake. So we have a very good track record. We're very reliable. That's their view, right? Only 1,000 are fake. And then most of them are DigiNotar ones, so in fact, this is only one incident. So we do a quite good job. So very, very interesting point of view. Okay, so I think it's... yes.
I gave a talk where and I was making a similar complaint, and the head of product marketing from Comodo was in the audience. And he basically said to the whole audience, look, we're a company too. We can only spend so much on security because we have to make a profit too.
Yes, exactly. That's the thing. So what are the incidents? So the Comodo incidents, so 9 fraudulent certs were issued by Comodo. And they say it's only 9, right? And we issue 2 million per year. Only 9 fraudulent certs. But of course, fraudulent certs allows real bad attacks, right? Then, of course, the big case was DigiNotar. You probably all heard of this. About 500 fraudulent certs were issued. So what happened is that, in fact, the PC, which actually controlled the hardware module, had no antivirus, no firewall, no protection. An Iranian hacker got in there and could issue 500 requests for certificates. How did they find out? Due to OCSP requests coming from Iran. And also Google does some checks about who issued certificates for it. And so it turned out that this Iranian guy used DigiNotar to issue certificates for Google, which are fake. And those certificates were then later used to actually, to a combination of a DNS attack and these fake certificates, to attack users in Iran and to intercept their connections to Gmail and Facebook and so on. And so probably people are in jail because of this attack. It's not a joke. It's a serious attack with major implications. Okay? So DigiNotar didn't survive this. They went bankrupt a few weeks after the incident was announced. And there is a very interesting paper by Fox IT, which you should really read to see what can go wrong. Okay? So apparently, it's an incident that played over the last 2 years. So there is a Turk Trust incident. So Turk Trust in Turkey also has been issuing certificates for Google.com. And so the whole official story is it's an error in configuration made during migration and backup. It's a mistake. I'm sorry, but I don't believe this. Right? So the Turkish government, again, could intercept communication. If you get a fake certificate for Google.com for a different Google.com public key, it actually means you can intercept communication intended for Google.com. And so it means you can actually intercept communication from Android phones, communication from people who want to read their Gmail account or the Google Plus account. You can actually intercept it and meet in the middle Google. So this Iranian hacker claimed he has hacked GlobalSign, but there is no evidence of this, and VeriSign as well. There is of course, the industry doesn't show you all the details of their incidents, right? So there is 1,000 keys known to be fake. We don't know how many thousands are, we don't know that they're fake, okay? So also Bit9 had a very big incident, and this is a company that provides software and network security services. It seems that they're not actually using their own security software, and so they lost their signing key last month. That's fun. So, but it shows that indeed what we have seen in this industry is a race to the bottom, okay? So you don't try to be very secure as initially and have secure solutions. What the business model is, try to save money. First you get rid of the dogs, then you get rid of the guards, then you get rid of the antivirus, then of the firewall, and you keep reducing your costs, and nobody notices anything. You see, your income stays the same, and your security costs go down, so your profit goes up, and so the board is happy, and the shareholders are happy. Of course, you have no security, but it's a small detail. So the government of Malaysia also has signed with their key malware. They also had 500-bit keys being certified, all these kind of weird things. So I don't have a good answer yet. So the CA industry, in spite of the claims that everything is great, what their representative says, they've actually responded, and they responded as they are in chaos, they responded in chaos. So as far as I understand, there is at least 4 initiatives, and I mean, I only saw the presentation last Thursday. I didn't have time to do more research. But in IETF, there is at least 4 initiatives to improve stuff, and one is DANE. And DANE has one weakness. It assumes that DNSSEC is widespread, which is it not. It has taken a long time to deploy DNSSEC, more than 10 years before the root was signed, but even now today it's not widely used. And so if it's widely used, you can actually protect your SSL. So with this DANE protocol, you can say that a given server, my server, can only get certificates from this particular CA. This would stop the attack on DigiNotar, because Google could say, we only want, say, VeriSign CAs or Google CAs. And so if your browser would see a certificate for Google issued by DigiNotar, you would reject it. Okay? So the comment of Google on this proposal is it would need a hard fail. If you then see certificate by something else, you should not accept it. Right? Otherwise, it makes no sense. Okay? Then there is authorization. This is you tell the CA that if you're not one of the CAs on this list, don't issue certificates for this domain. So this would be a slightly different approach. There, for example, you start your server, and you tell the CA, or you get help from the CA, and say, I only want certificates from Google or from VeriSign. Okay? So this is a message from the server to the CA. Of course, the problem is then you may end up in lock-in. Because if you chose one CA, it may be much harder to change your CA. Because once you then change the CA, you actually will make some certificates invalid, right? Your clients may be in trouble and so on. There is a similar mechanism for clients called pinning. It seems to me the easiest to roll out, in particular for the large servers. This is for clients, a message saying, you know, you've seen a Google certificate issued by Google or say by VeriSign. Okay? If you in the future detect another one, raise an alarm. In fact, and this is how many of the CA compromises have been detected, because there is already this feature present in Chrome that you actually check who issued certificates before, and if this CA changes, you actually respond. Okay? So, of course, if the comment by Google was that if you see an error, it's probably not because there is a breach, but because there is a misconfiguration. Yes?
My understanding is that Google will take certs for their pinning API, even from small sites, and share that data with Firefox. So I don't think it needs Bootstrap. It's just a matter of site operators going and...
No, but so that was a debate. So some people said it can only be done for large sites. But so indeed, Google is prepared, and some of the other players, but not all, are prepared to actually collect certificates from many sites. So in fact, that not only for the 5 big ones everybody visit, but also for thousands of smaller ones, you actually get preloaded certificates in your browser. But then, of course, you get revocation issues there as well, and maybe a hacker can change this. And so, and the final one is search transparency. This is kind of yet another thing. And this is actually something which is kind of baffling to me, that they still have to work on this. But the idea is the following. We're going to make public the certificates that are being signed. So at least if you, as DigiNotar, publish a certificate for Google, it will be public.
I don't understand that.
Well, today, if a server, a CA root signs a certificate, it keeps it private. It doesn't make it public in a public list which certificates. So in fact, if Peter Eckersley collects all the certificates, but you have to write a crawler for this that goes over the whole internet and finds those. There is no database where you can go to get all those certificates. And if you would have a database, then you would see who is hacking stuff. Okay? Of course, government don't like this, because if they are impersonating Google, right, and also companies do this, then of course they actually have a problem, right? Because then it becomes obvious. So this is, it would have stopped many attacks if you just had transparency. But of course, the industry is very worried as a competition issue, because it would mean that you could see who is issuing what, and you could maybe try to get each other's customers and so on. So from an engineering point of view, it's a no-brainer. But from a business point of view, it seems to be quite problematic. So what is interesting, so I went to this panel. I have long comments, which I still have to digest. But essentially, you see there is at least 4 approaches. And there is probably more. And then for some of those approaches, like pinning, there is 2 solutions, okay, by different vendors. So you see that every vendor, either browser companies or CAs, have their own approach of solutions. And some help. And the problem is that technology-wise, they probably all have advantages and disadvantages, but there is always this interference with business issues. And that's the big problem, because it's a big business still. And so for this reason, it's a big chaos. And it's not that the industry can agree on 3 major improvements and let's make them now. Pinning seems to be the one that can be rolled out quickly and is being rolled out. For all the other things, you have to wait for the NSSEC, or people say, well, in 5 years we'll be done with rollout, these kind of things. So don't expect a quick solution, and it's still a very big chaos out there. That's the main message of what I got from this. So of course, we discussed this. Of course, if your server key is not in a certificate recognized by your browser, you get this kind of error message. And then, of course, you actually have to decide what to do. And of course, as a cryptographer or as somebody who went to this course, you can start looking, okay, this is not in the browser, but this is a certificate, and so on and so on. I'm going to accept this or I'm not going to accept this. But of course, ask this to your grandmother or your mother. I mean, this is Chinese to them, right? I mean, this is completely hopeless. Okay, so I guess the summary is there is no easy fix. Technology-wise, it would be kind of easy to improve stuff, but because of all the competition and business issues, everybody wants different solutions. And for example, Google has both a browser and a server, and so they have a very different view than people who only have browsers or only have servers. Okay, they can do different things. So don't expect quick fixes or easy solutions, but some basic improvements will be replaced. And so I guess I'm not easy to call for regulation, and I guess for this reason of independence and reduced government control, I was always against regulation. But if you see what the mess the CIs make, I think they should be regulated. There is also a very big debate about whether people should be allowed. So some governments insist that they can impersonate. So the Chinese government obviously wants to impersonate all the major servers. So, and they keep pushing IETF for offering this service. Also companies, by the way, companies who do deep packet inspection, they don't like SSL connections to their firewall. So they, in fact, what they do is they impersonate, they put a fake CA certificate in the browsers of their people, and they meet in the middle all their employees' systems. It's quite unethical and also quite insecure, because you open yourself up to other attacks, yes?
Will you discuss the Trustwave Mozilla incident around Trustwave selling their CA cert for data protection? Or any thoughts on that?
Well, I haven't studied that one in detail. I've seen the things, but I'm not going to discuss it. But indeed, there is more stuff to be done. Okay. But I just want to wrap up, because I'm running out of time. So there is many trust models. There is the PGP model, where you sign the public keys of your friends. Okay, you kind of this web of trust. This is great, because it really works, and you don't have to trust anybody else. It's also a disaster, because if you're not a security expert, you don't know how it works, you don't understand it, and revocation is a nightmare. Right? If you issue new keys every 5 years, after 20 years, you have 4 keys which are everywhere over the world, and there is no way you can revoke them. Well, there is, of course, they have now kind of servers where you can do this, but it's still kind of problematic because it's not hierarchical. So the real problem is in revocation. I will skip that here. I mean, the general discussion. So I have to say something about this, which is very important. So what we have today is mostly invalid certificates. So we have actually CRLs and optimizations, and we have OCSP, which is online information. So CRLs is offline once a day. OCSP is every time you need to check. Now, of course, for performance reasons, there is caching of OCSP, which comes very close to CRL. And there is also CRL refreshing every minute, and this is very close to OCSP, right? So you can actually, depending on your network infrastructure, do both and be more or less secure. People have also proposed the opposite, whitelisting. So you would have a certificate only valid for an hour, and you get a new one every hour. But I'm not sure this works for most systems. So CRLs are kind of simple. To give an example of potential problems, in Belgium, so we have about, I think, 5 or 6 million identity cards. and about 1 person in 4 decides not to use their key pairs. So, but the way the system works is the key pair is generated and put on hold, and then when you get your identity card in the commune, the public key pair is activated, but if you choose not to activate it, it remains revoked. This means, in fact, that Belgium has about more than 1 million revoked certificates. The CRL is huge. Plus, it keeps growing because, of course, if public keys roll over, people get new identity cards. So this is a quite big deal. And so, in particular, for mobile applications or lightweight applications, so the Belgian CRL, the full one is several megabytes, which was something we warned the government about, but they decided to take this approach anyway. So OCSP, this is kind of nice. As I told you, you do query a CA or a delegate of it. You send it the hash of the public key in a certificate, the hash public key in a CA and a serial number, and you get an answer which says good, revoked, or unknown. And you also get information on the freshness of this answer. But there is a fourth possibility, which I don't have on this slide, namely no answer. And if there is no answer, it's assumed to be yes. This is how all the browsers work today, because you don't want to break the internet. And so when you criticize the vendors about this, also about the other things, the answer of Commodore was, well, you can't change the wheel on a bicycle when it's riding. That's their answer. So the problem is that the CA system, however crappy it is, it's now massively in use. And any change breaks a small part of the web, and nobody wants to be responsible, in particular, in a competitive environment. So if a browser company moves first, they will lose market share. So they have to move together, and they seem to be unable to agree to move together. Or they occasionally move, but very, very slowly. Okay, so this slide mentioned this, that in fact, well, 2 things. So you may get old information freshly signed. So you may have a CRL updated every week, but you get a by-the-minute correct OCSP response. What does that buy you? And so the other thing is no answer means, in fact, OK. So it's very simple. If you see as an attacker, if you see a negative answer, you just suppress that, and then the browser will say OK. It's still the major problem. So for the final few minutes, so trust models, who is involved? Who certifies public keys? How are trust relationships maintained? How granular are they? And how do they support existing business models or societal models of trust? So in Europe, this is, for example, very clear that in Belgium, identity cards and public keys are issued by communes, by local authorities. In Greece, it's by the police. In Sweden, by the post. In Norway, by the banks. So depending on who you trust in society, you actually get different ones. In Germany, there is 3 separate ones, one by the communes, one by the employment agency, and one by the health agency. So it depends on who you trust, and you cannot just come with crypto and create new trust. And I think this is the big problem of all these CAs, that they say, I'm verified, trust me. Why should you? Okay. So granularity, of course, hierarchical, the Visa model is, you also trust Visa. There is not much granularity. In the browser, you have to trust 650 or 65 companies. In the personal model, you can choose in BGP who you trust and who you don't trust. Okay? There's more granularity. In business to business, of course, the enterprise model is much more suitable because there is no hierarchy between companies. And the other 2, I would say, are more or less in between. So there is no easy choice for a trust model. It depends on where you're going to roll out your public keys and what you're going to do with it. Okay, and this is more or less the wrap-up. So the personal model is OK. I mean, if you have a standardization body of 8 or 10 people and you meet every 3 months, it's fine to actually, in the meeting, share public keys and later on use this. And if a guy leaves, to revoke him, and if a new guy comes, to add them. So on a small scale, it works. Okay? The browser model, well, I don't think you can say it works, but on the other hand, it does work because there is people making money, and e-commerce works. So as a security person, I can criticize the decisions, but on the other hand, some people get something out of it. Okay? So the hierarchical model, I mean, Visa has proven it works, and MasterCard. So in the financial sector, it seems that some people actually are in charge and can make the rules, and this works. And I guess this is the nice thing, that we don't need to have 75 cards if we go to 75 countries. So there is some benefit to having a hierarchical system there. So between peer organizations, so in an industry sector, for example, like pharmaceutical or automobile, I think the enterprise trust model works quite well. And you have a lot of flexibility, but also, unfortunately, the complexity that goes with it. And so global PKI, so people said after the PKI high, PKI is dead. But if you understand crypto, you know PKI cannot be dead, because you can't do crypto without public keys. So it's just that I think we have a very hard time figuring out how to distribute public keys. And the problem is that the most visible model is the browser model, and this is kind of broken in many ways, but it's very hard to change it, because it's just so popular. And assume that, say, all the major internet servers would say, we're now going to only accept browsers with certain security levels, then people will not be able to get there, right, with their old browsers. So the problem is you can't break the internet anymore, because people get very, very unhappy if they can't access their funds, or they can't book their travel, or they can't read their email. So this is the problem with security systems. If they're not successful but secure, nobody cares. And if they're successful, you always keep finding small security problems, but you can't fix them anymore. So only if there is major problems, they will do something, or they will at least, the industry will act as if they do something. They will have this security theater. But it's very hard to change reality, because it's just too important. That's my summary of PKI. So unfortunately, I had no time for identity-based encryption, but I'm very happy to actually explain to you over lunch why it doesn't work. OK. Hope you have a nice lunch. Thank you very much.